Hi everyone, my name is Rakshan and I'm an MD, PhD, MBA student. Dr. Walker and I have prepared this presentation on AI and radiology. So these are the learning objectives. Through this talk, we will answer questions including what is AI, how has AI developed over time, key terms in AI, and diving into how AI is used in radiology today, limitations of AI, and what the future might look like of AI in radiology. So let's start with a definition to make sure we're all on the same page. Artificial intelligence is a broad scientific field which aims to basically get computers to perform tasks that would normally be done by humans. Artificial intelligence has applications for reasoning, communication in natural language, processing information, and even with prediction capabilities. You probably have seen AI in action and were not aware of it, like when you use Netflix or Amazon Prime. So for Netflix, you probably have seen the recommendations page. Netflix provides recommendations on shows and movies to watch based off of your previous watch history and comparing it to other users like you using AI. For Amazon, Amazon Prime has a feature called X-ray, which uses image detection to identify actors on screen and then links information like their bio or IMDb page. So AI is something that is already here and integrated in many of our day-to-day lives. But what about its applications in radiology? So on this screen is a quote about an individual's position about AI in radiology. It reads, "There is no function that the computer cannot do in radiology." Take a guess at who might have made the statement. It was actually stated by an academic radiologist named Dr. Gwilym Lodwick in the 60s. He predicted that computers would replace radiologists. We all probably know watching this video that Dr. Lodwick's prediction of computers fully replacing radiologists did not come true. So what happened from the 60s until now? In general, the concept of AI was first established by Alan Turing in 1954. Since then, new methods were developed to advance artificial intelligence. In the 60s, the first chatbots were released, which were capable of carrying out human conversation. In the 80s, we saw the first computers carrying out reasoning tasks, and in the 90s, we saw neural networks, which had applications for handwriting and speech recognition. However, there was one issue with all the advancements and algorithms being developed. In the 1990s, improvements in AI began to slow down because of limited neural network performance, and computers were not as powerful as they are now to handle complex computing tasks. Now, computing power has increased, and a lot of the methods and algorithms developed in the 90s are being used currently. Researchers call this a rediscovery of AI because a lot of the applications of AI we see today use methods that were developed decades ago. And in 2007, we started to see applications of AI seen here from ImageNet, where a computer can look at an image and intelligently and accurately label it. For example, a computer was able to look at a picture of a dog and identify it as a dog, and was even able to specify the breed of dog, for example, Husky. So if we see ImageNet classifying images accurately, can a computer look at diagnostic images and then also give us an accurate label of what's going on? Before we answer this question, let's go over some basic terminology. The terms deep learning, machine learning, and artificial intelligence are used frequently in this field, and they are all related. AI methods in general are based on computer algorithms. An algorithm is a step-by-step instruction for solving a problem, and they can range from being very simple to very complex. So, starting with machine learning refers to AI methods where a computer learns from experience over time. An example of this is training your Outlook to sort emails into the spam folder. Within machine learning, we can break this down into supervised and unsupervised learning. You can think about supervised learning like learning with a teacher. In supervised learning, a computer will learn based off labeled images in a training dataset. The computer will study the labeled images and then be able to label a brand new image presented to it. In radiology, this is like having AI learn how to identify pneumonia by studying labeled images of pneumonia on chest x rays. In unsupervised learning, there is no teacher, meaning there are no labeled images. Here, an algorithm will group data based on similarities. This is helpful because there is some data which is very difficult for humans to interpret. For example, it's easy for us to imagine a graph with two dimensions, like an x and y axis. It gets harder to imagine a graph with three dimensions or an x, y, and z axis. And it's almost impossible for us to think about a graph with 50 dimensions or 50 different axes. This is where an unsupervised machine learning can come in and use algorithms to transform the data into something that's more easily interpretable for humans. Unsupervised machine learning can help identify unexpected relationships, and it's used a lot to drive research and discovery. So now that we've covered machine learning, let's move on to the next term, deep learning, which is a subtype of machine learning. Deep learning can help to identify hidden and complex patterns in a dataset, where machine learning techniques like supervised or unsupervised machine learning can then use to classify the data. Deep learning uses a combination of layers, and that's why it's called deep, to identify for pattern recognition and prediction, and its applications have led to advancements like self-driving cars. Each layer will identify different features in a dataset, and combining the layers can lead to identifying complex patterns. In what we talked about before with machine learning, usually we need labeled images or data, which then get transformed into math, which computers understand. Deep learning is different because it eliminates the need for manually selecting features. Deep learning methods automatically detect features of a dataset and define relationships between them in mathematical terms a computer understands. Deep learning algorithms learn from thousands or even millions of examples, making them extremely accurate at the prediction task they're designed for. Sometimes deep learning will make predictions which are correct, but we don't understand why because it's difficult to understand all the patterns used to arrive at a prediction. Because of this, deep learning is sometimes called a black box. Finally, one last term is natural language processing. This is used to understand communication, which can be written or oral, like chat boxes or Amazon Alexa. Most natural language processing uses deep learning, and it is being used to reproduce human communication. So, how are all of these terms and methods used in radiology today? So, in radiology, there are a few main applications of AI, and this slide gives an overview of two main applications with an image from Hosny et al. This image is giving a summary of that using the example of a lesion seen on the lungs on the left side of the slide. The first application, or the top box, relies on engineered features from regions of interest based on expert knowledge. This can include texture, volume, and shape. The features that are most helpful in classifying the image are selected and fed into a machine learning classifier. The second box below gives an example of using deep learning, which we now know does not need labeled images. Several layers extract, select, and classify the image simultaneously. Using this method, patterns we did not think about, like abstract lines or shadows, may be used to learn about the image and its classification. Both of these methods are known as branches of radiomics, which is a radiology research field. Now, let's move on to practical applications of AI in radiology, starting with pneumonia detection. So we know that chest x-rays are a robust method of diagnosing pneumonia. An algorithm was developed called ChexNet by Raj Prakar et al., which can detect pneumonia from chest x-rays at levels exceeding practicing radiologists. The algorithm was trained on over 100,000 labeled images. One application that the developers hope from this is bringing radiographic interpretation to parts of the world which do not have access to radiologists. Two-thirds of the world's population does not have access to radiology diagnostics, and this algorithm is one way to increase access. AI has also been classified or applied to classify interstitial lung disease on high-resolution chest CT. This image is showing us healthy lung tissue in the top two rows and pathological lung tissue in the lower two rows. This group, Huber et al., used AI to create mathematical vectors of honeycombing, which is a morphological pattern related to a heterogeneous group of interstitial lung diseases. The AI used images which were a length of 23 pixels, with each pixel measuring 0.69 millimeters. The AI was able to classify healthy and diseased tissue using quantitative measures based on the texture and characterization of pathological patterns in interstitial lung disease. Beyond the lungs, AI has also been used to predict mechanical bone stability and fragility by analyzing bone trabecular structure in CT and MRI datasets. So this application is going beyond just labeling an image. It's AI using the image to also predict the risk of a fracture. This is an MRI image of the proximal tibia. It's a sagittal reconstruction, and the anterior surface of the tibia is visualized, which shows the complex trabecular bone structure, which are the gray lines, surrounded by bone marrow fat, which is the bright tissue. Two holes, which are the dark circles in the image, were drilled to fix the position of the bones during imaging. The Huber et al. Group used images like this one. Then geometric properties of the image were analyzed using a method called the scaling index method, or SIM, which gives the local geometric properties of an image. The shape and neighborhood of each bone voxel was characterized. A nonlinear histogram of the SIM image was used to extract local geometric features. The SIM features were used to predict biomechanical properties of the bone with high accuracy and also characterize differences in spatial chondrocyte organization in the radial zone of the cartilage matrix by advanced geometric structure descriptors. This is important because it can allow for non-interventional monitoring of osteoporosis progression, and we can use these quantitative biomarkers to predict fracture risk. These methods outperformed currently used measures of bone mineral density in their paper. AI has also been applied in early diagnosis of small breast lesions. Breast imaging is known to be notoriously difficult to interpret, and this is one way where AI might be able to help. This application of AI also builds on the concept that there are some differences in images which are hard to see from the human eye, but the computer can see. A dynamic analysis of lesion morphology was done using feature extraction and machine learning techniques by the Nagarajan et al. Team. The images analyzed were very small, 11 by 11 pixels. This was chosen to minimize the amount of surrounding healthy tissue included in the image. This approach is being validated further, and the hopes are that it can assist radiologists with evaluating between harder to discern malignant versus benign lesions. AI also has been applied to help with more tedious tasks like assessing bone age. The Larson et al. Group developed a deep learning model to estimate bone age based on comparisons to the Grulich and Pyle atlas. The model used over 12,000 clinical hand radiographs and corresponding clinical radiology reports. The model was able to estimate bone age as well as trained human reviewers. Now, there are also key limitations to AI. One main limitation with AI is based off the quality of the data sets it is trained on. For example, here's a photo of Prince William right after the birth of one of his children outside the hospital. It looks like he's giving the middle finger to the press. But we know in radiology that we usually need multiple views to make meaningful conclusions. And in this image from a different view, we can see that Prince William was actually holding up three fingers to show that he now has three kids. A human can swap between different views and even different types of scans to make a conclusion, but AI algorithms may not all be able to do this depending on how they've been trained. And there are also other key limitations to AI. Because a lot of the AI approaches we talked about rely on training from pre-existing data, AI can worsen existing social inequalities by duplicating or worsening race, gender, and other biases in data sets. AI algorithms are only as good as the data they're trained on, and some people may have better access to healthcare than others. Training AI on algorithms representing people who are underrepresented can be one way to reduce bias with minority groups. Also, AI does not exist in a vacuum. There are still questions around the legal implications of AI in radiology, who is responsible and in control of it, and regulating AI. Further, there's also discussion around socially responsible AI, which can benefit everyone and not just a few people. So where do we go from here? If you type in AI will replace on Google, you can see that radiologists and doctors are among the top suggested search results. And bold claims are made in leading scientific journals about robot radiologists, AI replacing doctors, and even anxiety from fear that AI will cause us to lose jobs. However, we still don't see robot radiologists around in the hospital or even completely self-driving cars, despite bold promises. And this is interesting because if we remember, a lot of the AI we use today is based off of algorithms from the 80s and 90s. And in the early 2000s, development in AI slowed down largely in part due to limitations in computing speed. Are we currently in a similar period of plateau due to structural limitations on AI's capabilities? And a lot of the claims around AI replacing radiologists are rooted in some misunderstanding of what radiologists are doing. Radiologists will routinely discuss cases with other colleagues, perform bedside procedures, and sometimes perform interventions. The idea is that AI will help assist with mundane tasks like measuring lesions in the lung, so radiologists can better manage their time and high image workloads and possibly spend more time looking at sophisticated lesions. It's also postulated that AI in radiology will help improve the lives of patients more through predictive capabilities based off of imaging and non-invasive biomarkers for disease. Another very applied application potential of AI is to analyze raw data and sinograms. We know that the images we see of CT scans shown on the left two columns are recreated based on raw sensor data in the form of sinograms shown on the right two columns. It is not possible for a human to look at a sinogram and analyze it ourselves, so we analyze the recreated CT image. However, creating a CT image from the raw sinogram results in data loss. Efforts are being done to use AI to be able to read raw sinograms to reduce the impact of data loss on image interpretation. The next steps are now to advance AI education, efforts from government, academic, and industry organizations working together, and refinements to validate AI. Thank you for listening.